He's also a gifted nature photographer, I guess. You call him a nature photographer who focuses on picturing the beauty of Alaska. And I've asked him to share some of that work with us at the end of the presentation, and particularly any night sky work that he's done up there, auroras, and my favorite mountain, Denali. So with that, we'll turn it over to Dr. Rector. I want you to hold your questions probably until the end of the presentation, and then we'll be able to ask them. So everybody place themselves on mute, and Deb and Paul have started the recording. So Dr. Rector, I think turn it over to you.
Okay. Well, thank you, Bob, and thank you, everyone, for coming today. Thanks, Bob, for the invitation to speak to your group. I've lived in Arizona off and on over the years, so it's nice to be here today with you all. So I'm going to talk for probably about 45 minutes, and then I'll leave time for questions at the end. So as we go, feel free to think of whatever questions you might like to ask. So my name is Travis Rector, and as Bob mentioned, I'm a professor at the University of Alaska in Anchorage. And you probably don't know me by name, which is totally fine, but I'm hoping that maybe over the years you've seen some of the images that I've made. These are just some examples of images that I've made using the telescopes at Kitt Peak and elsewhere that I'll talk about. And I have, last I checked, I have over 80 APOD credits to my name. And one of the things that I do is I make many of the astronomical images that you see coming from professional observatories like Kitt Peak and the like. So just a little bit about my history. Like many people, I started doing nighttime photography or astrophotography using traditional film and camera methods. Started in the early 90s, but really got serious about it in the mid 90s, and especially when Comet Hyakutake came by. In fact, this is a picture I took of Hyakutake from Mormon Lake, not far from where you guys are. And then with Comet Hale-Bopp, I got even more serious about the photography. And at first I was really interested in landscape photography with astronomical phenomena. It seemed like this was the kind of imagery that really appealed to people, the types of photographs that could give you a sensation of being in this place, but still being able to enjoy this amazing sky. And over the years, I have continued to do some landscape photography, mostly of the observatories that I've gotten to work at, and especially ones that show interesting optical or atmospheric phenomena. So for example, here's a picture of Kitt Peak at sunset. And if you look over on the right, you'll see the pyramidal shape of the shadow of Kitt Peak that it is casting over on the valley floor below it. So over the years, I've been fortunate to use telescopes at many different observatories around the world. And at first I would, so one of the things I've tried to do is to document photographically what it's like to work at many of these places and take photographs of the telescopes and the surroundings around them. I moved to Alaska about 18 years ago, and I don't actually do as much wildlife photography as I used to do, in part just because I don't have the time, but also because there's a lot of amazing photographers up here. But I do like to, whenever I get a chance, take advantage and take photographs of my beautiful state, and in particular that of the aurora, either using traditional film photography, or in recent years, I've been actually doing more digital work, and in particular using fisheye lenses. Our observatory has a planetarium, and so we recently made a show about what it's like to watch the aurora here in Alaska, showing the best of the best footage, as well as you don't have to stand outside and 40 below zero, which is the temperatures that we had to endure for some of the photography that we've done. So I graduated from the University of Colorado with my PhD in 1998. And after that, I went to Kitt Peak to start working there as a research scientist. And at that time, I was still very much doing wildlife photography and night sky photography in general. But this was really my first opportunity to do deep sky photography with telescopes. And at that time, Kitt Peak had just built a new wide field imaging camera called Mosaic, which is shown in the picture here, attached to the bottom of the 36-inch or 0.9 meter telescope on Kitt Peak. So Mosaic was a a new generation of wide field digital imaging cameras. It was an 8K by 8K or 64 megapixel array, which even by today's standards is pretty darn nice. But back in 1998, when it was completed, it was huge. It was the largest digital camera of its kind. And so when this camera was built, we wanted to show off the relatively wide field imaging capabilities of this camera. In particular, when this camera is mounted on the 36-inch telescope at Kitt Peak, it has a 1 square degree field of view, which for a digital CCD at the time was enormous. So we wanted to show off the image. We wanted to show off its field of view. And so I had the idea of making this image. And that is, I took a picture of the moon, waited for 2 days for the moon to move out of the way. And then I took a picture of the same location in the sky again. And then using Photoshop, superimposed the 2 images together. And so this is just to show off the relatively wide field view of the camera. Now, at the same time, I also took other pictures. And so, for example, the second image I ever made was of the Rosette Nebula. So these 2 images are to scale. And one of the things I like to emphasize to people is that many pictures of astronomical objects are of things that are relatively big. You could, in principle, see this object in the night sky if it were simply bright enough. So I made these 2 images for Kitt Peak, and they liked them, and they asked if I'd be willing to do more. And that's when I learned a very important lesson in life, and that is if you do something once, it's a favor, and if you do it twice, it's your job. And so I continued to make images for Kitt Peak, and then I also started making images for our sister observatory down in Chile. This is a picture of Cerro Tololo Inter-American Observatory in the Atacama Desert of Chile. And at the same time that I was doing that, the Gemini observatories were being built as well, one in Chile and then also one in Hawaii. And so I make images for them too. Now, after being at Kitt Peak, I then went to work here at the Very Large Array Radio Telescope in New Mexico. And actually, my origins in astronomy were in radio astronomy. And I started making color composite images for them as well, using radio waves, which brought up all sorts of interesting questions about how do you make color images when you were looking at radio waves. So after this time, I came up here to the University of Alaska, and I've continued to do this work. And over the last 20 to 25 years, I've made over 300 images from different observatories. So why do we make these images? Why would a professional observatory engage in astrophotography? Well, the first and most common reason is to visualize scientific results. If there's been a new scientific discovery that we'd like to, from our observatory that we'd like to feature, we try to make a color image to go along with the story to help people visualize what it is they're hearing about. The second is often just to demonstrate new technologies. If we've built a new camera or maybe a new adaptive optics system, we want to show it off, show what its new capabilities are. And a very small fraction of our time is actually given to us at the telescopes just simply for the purpose of choosing things that we'd like to look at for fun. So in a typical year, about 330 nights at one of our observatories will be clear enough skies to do observing. And typically we get maybe 1 or 2 of those nights. So we get a very small fraction of the time on the telescopes. And so we use this time just to make images of things that we think would be beautiful. So here's some recent examples. This is a color composite image we made using data from what's called the DESI Legacy Survey. And so this is a press release from an organization called Noir Lab, which is the new name for the organization that combines Kitt Peak, Cerro Tololo, the Gemini observatories, as well as the new Vera Rubin Observatory, which is being built in Chile. So this is an example of how we create a color image just to show off this new data set. Here is another example that we recently did, and this is to show off the adaptive optics system on the Gemini South telescope. You can see a picture of this nebula on the left without adaptive optics and what the same nebula looks like with the adaptive optics system operating. And then finally, as I mentioned, we get a very small fraction of time on our telescopes, just simply for the purpose of making color images. And to do this, what we do is we just comb through various catalogs and whatnot, and we try to find objects that we think that maybe there isn't, that maybe we can make a really nice image that is of a higher quality than things that already exist out there. So that's one of the fun challenges, is finding new targets. And it's getting harder and harder, I'll say, because amateur astronomy images are getting so darn good that whenever we find an object, I often find that there's an amazing amateur image that we feel like would be hard to beat. So that's kind of the fun of it. Now, I've been doing this, as I said, for over 20 years. And during that time, I've had an opportunity to talk with people about the images that we make. And it seems like 9 times out of 10, when people ask me a question about the images, the first question I get asked is about whether or not the image is real. So people often ask questions like, is this what it really looks like? Or are the colors real? Or one of my favorites is, if I were standing right next to this, is this what it would look like? Now, I don't really know what it means to stand right next to a galaxy or a nebula, but I think the key idea here is that people want to know if they were closer to it, if this is what it would look like. And so basically people want to know, is the image they're looking at real, or is this just some sort of computer graphics that's been generated just like, out of a Star Wars movie or something like that? Now, with some exceptions, with the exceptions of some objects here in our solar system, like the planets and moons and things like that, the answer to this question is almost always no. These images aren't what it really looks like, but I want to explain what I mean by that. So let's go through an example. So this is a picture, of course, of the famous Horsehead Nebula. This is an image I made with the Mosaic camera on Kitt Peak many, many years ago. And so let's imagine you were to get in a spaceship and fly from the Earth out to the Horsehead Nebula, several thousand light years away. But once you get there, let's imagine you looked out the window of your spaceship to see what you would see. Well, this picture doesn't show what you would see, but this picture is a pretty close representation to what your eyes would actually see. So you would see some of the stars, but you wouldn't be able to see any of the nebulosity. And the reason why that is simply because the nebula is too faint. And even though you get closer to it, the nebula doesn't get any brighter. This is something that's called surface brightness. Surface brightness is a ratio of how much light is coming from an object to how big the object appears. So as you get closer to the nebula, you're getting more light from it because you're getting closer. That's the inverse square law. But the nebula is also getting bigger. And so those two cancel out. And so the nebula will not actually appear any brighter. And this is a game you can play at home. As you walk towards the wall, you'll notice that the wall gets bigger, but it doesn't actually get any brighter. And so what that means is that if there's a nebula that is too faint for you to see with your eyes from here on Earth, you still won't be able to see it, even if you get closer. Now, this picture that I'm showing you of the Horsehead Nebula was taken with this Mosaic camera. So it is on the same scale as the previous 2 images I showed you. So the Horsehead Nebula is actually plenty big. If it were bright enough, you would easily be able to see it in the night sky. It would look bigger than the moon. But the problem is simply that it's too faint. So if you really want to see what our deep sky objects look like, we could show you pictures like this, but that's not very exciting. So the whole idea here is that we use our telescopes to make images of objects that show them not as our eyes see them, but as our telescopes can see them. So in other words, our telescopes are designed to give us superhuman vision. They can show us things in ways that our eyes cannot. So the answer is always no, but this is for a variety of reasons. One is, as I mentioned, the surface brightness is constant. Another is, as you probably know, our eyes are really bad at seeing color in faint light. There's only a handful of stars like Betelgeuse and Rigel where you can actually, the stars are actually bright enough for you to see their color. The rest just look black and white. It also turns out our eyes are really bad at seeing some colors. In particular, our eyes are very bad at seeing red light, which is why we use red lights around observatories, so you can keep your dark adaptation. And then finally, there are all these kinds of light that our eyes cannot see. So things like X-rays and infrared light and radio waves. And so our eyes are really amazing tools for being able to see things during the daytime, but it turns out they're really lousy for doing astronomy. So when it comes to all these other kinds of light, we build telescopes that are able to see them, so that way we can get a more complete view of what the universe looks like. So when it comes to the goals of a telescope, there's many things that telescopes do, but I think the three primary goals, the first is the most obvious, which is just to magnify an image, make something that looks small appear to be bigger. And this is what usually people think about when they think about telescopes. So that is, they imagine that a telescope makes something far away look close, just like if you were at a basketball or a football game and you were up in the cheap seats and you wanted to use binoculars to see what it would look like if you were down closer to the field. But telescopes also amplify. That is, they can make things that are faint appear to be brighter. And so we use telescopes with large mirrors to do just that. And then finally, to expand our vision, to see these kinds of light our eyes can't see. And so just to put things in perspective, this is, of course, the human eye. And the aperture for the human eye is very small. At its most dilated, it's only about 1/4 inch wide. For comparison, this is the mirror, the primary mirror in the Gemini 8-meter telescope. And for perspective, that is a human in a clean suit standing in the middle of the mirror. So this is 8 meters across. And what it means is that at any given moment, this mirror is collecting over 1 million times more light than what the human eye can see. But not only that, we can do long exposures. We can do, our eyes are designed to work like a camera where we take 30 seconds, basically 30 exposures a second. So for any particular image that we're seeing at a given moment, we're only seeing 1/30th of the light. Whereas for these telescopes, we can collect light for many hours. And perhaps the most extreme version of this is what's called the Hubble Extreme Deep Field. Now, because the Hubble is in an orbit around the Earth, it doesn't have to worry about the atmosphere. So the sky is basically as black as it's going to get. And so by just simply looking at a single location in space for a long period of time, you can see extremely faint objects. And so in this image right here, you can see there's the little square near the center of what was called the Hubble Extreme Deep Field. And what they did is they stared at this location in the sky for many days. And in doing so, they were able to take what is essentially the deepest astronomical image ever made. So what you're seeing in this picture here are all these faint little smudges that are extremely distant galaxies. And so the most distant, the faintest objects in this image are about 100 billion times fainter than what the human eye can see. So by using telescopes in this way, we can see things that are just simply much, much too faint for our eyes. Now, when we make color astronomical images, we use electronic detectors that, for the most part, actually can't see the actual colors of light. So when it comes to optical and infrared cameras, they only can measure the brightness of light that is hitting the detector. So if we want to create a color image, we have to mimic color the same way that the human eye does. And so the human eye produces a color image using what's called the 3-color or tricolor method, which is there are detectors in our eyes called cones that can see red, green, and blue light. And the way they can tell what the color of an object is by the relative amounts of those kinds of light. So my sweater right now looks green because your brain is getting more light detected by the green cones than the red and the blue. Now, we can mimic this when we take pictures in astronomy. We can use red, green, and blue filters that are very similar to the range, the wave bands that the detectors in our eyes can see. And these images are often called natural color images. And so this is an example of a natural color image. And this is basically the way you might see an object in space if you had gigantic eyes that could collect light for a long period of time. But one of the really cool things about astronomy is we have all these other kinds of filter that can see kinds of light that our eyes not necessarily can. So we have filters in the ultraviolet, we have filters in the infrared, and we also have special kinds of filters that you probably know about, things like the hydrogen alpha filter, which is designed to see a specific color of red light that's produced by hydrogen gas. Now, in this plot right here, it gives examples of 4 different kinds of filters we use. And I'll point out that right next to hydrogen alpha is another color of red light produced by hot sulfur atoms. And these 2 colors of red are not different, cannot be differentiated by our eyes, but by using filters designed to select these specific kinds of red light, we can tell the difference between what the hydrogen gas is doing and what the sulfur gas is doing. And so what it allows us to do is it allows us to create color images using more than the traditional red, green, and blue filters. And so these 2 images here show a nice comparison of those 2. So the picture on the left shows a galaxy just seen through red, green, and blue filters. And the picture on the right shows the same galaxy, but now seen through 8 filters. And so by using more filters, we're able to increase the amount of detail we're actually able to see in the galaxy. So how do we actually do this? Well, we'll take pictures through the many different filters that we have. And for each filter, we then assign it a color. Now, this is a picture of the Triangulum galaxy as seen through the blue filter. And this is the same galaxy seen through the hydrogen alpha filter. So you can see that in each filter, it looks very different. And then the next step is to assign a unique color to each filter. So in this case, I assigned red to the hydrogen alpha because that is its natural color. But the next filter we used was a filter that sees in the infrared, so a range of light that our eyes cannot see. Now, a good question to ask is, well, what kind of color should I use for light that's invisible to our eyes? But what we often do is use something that's called chromatic ordering, which is that we make the lowest energy forms of light that we see on the red end, and then the highest energy forms of light on the blue to violet end of the spectrum and everything in between. Now, in this example, I've already used red for the hydrogen alpha filter, so I want to use a different color. In each of the images we make, we use a different color for each filter. Now, since I've already used red, I'm going to use orange for the infrared filter, and then I'll use yellow for the R band filter, green for the green filter or V band, B for the blue, and then for the ultraviolet, I will use violet. Now, again, this is a range of light that our eyes cannot see, but our electronic cameras can. So there's 6 filters here, and when I combine them all together, here is the final color image of the galaxy. And if I zoom into the upper left corner, you can see that in this image, not only do we see the hydrogen alpha clouds glowing in the galaxy, but we can also see the colors of the stars very nicely. Now, in this example, this is an image that's used strictly for aesthetics as a pretty picture, but astronomers do actually use the relative brightnesses of the stars in the different filters to determine what the temperature of the star is and other things like what kinds of elements are inside the star. So there's a lot of information encoded in these images. Now, we actually do the exact same thing when we look at other kinds of light. So this is an example of an image that's made entirely with infrared light. Now, again, these are kinds of light our eyes cannot see, but we use the same principle of chromatic ordering. That is, we make the lowest energy light red, the highest energy light blue, and then everything else in between in the right order of the rainbow. So the lowest energy light we made red. The next one up was green. And in this case, we have 4 filters. We made the third one cyan, and then the last one is blue. And then when we combine them all together, this is the final color image. Now, in this case, all of the light you're seeing here is infrared light. So this is, again, not seeing the kinds of light your eyes can see, but it works in the same way that our eyes do. That is that when we see redder objects, these are objects that are preferentially emitting lower energy lights, and the blue objects are objects that are emitting more high energy light. So the same as it is when we look at light with the visible spectrum in our eyes. So one of the amazing things is that we have this incredible ability to make images using all these kinds of light, many of which do not correspond to what our eyes can see. And we have all these kinds of filters that see things differently than our eyes can. Kitt Peak has like over 100 different filters available for the telescopes up there. So when we started making these images, we had to ask ourselves, well, what are okay ways to make these images? Are there things that are okay to do and things that are not? And so one of the things we started learning more about is the way that our brains interpret images. And so this is an example right here. This is something that's called visual grammar. So this is something that's been known in the art world for a very long time. And visual grammar is just basically the way that our eyes and brains interpret an image. Now, you may not realize this, but whenever you look at something, your brain is trying to process the image and create a three-dimensional model of what it is you're seeing. And many optical illusions that exist are based upon the brain being short-circuited or being tricked into thinking something that's not real. So visual grammar is the way that our brain looks at an image and is able to determine what's going on. So this picture right here shows a vineyard here on Earth, and we can easily look at this image and get an understanding of what it is we're seeing. We naturally understand that the top half of the image is further away from us than the bottom half. And there's a lot of visual cues that help us to figure that out. So for example, the shapes of the leaves, we know that if we see two shapes that look essentially the same shape or color, but one of them is smaller, our brains will naturally interpret these objects as being intrinsically the same size, but the bigger one is closer to us than the one that's smaller. But another really important visual cue here is the atmosphere. So when we look at the hills off in the distance, you'll notice that the further away they are, the bluer they look. And that's because the Earth's atmosphere is scattering light and causing the sky, things off in the distance to look blue because light from them is coming through the Earth's atmosphere. So our brains naturally interpret things that are bluish in color to be further away than things that are reddish or orangish. And just as an interesting aside, when the Apollo astronauts went to the moon, they had difficulty understanding what it was, what they were looking at on the surface of the moon because there was no atmosphere and they didn't have this visual cue. So there's a famous story about the Apollo 14 astronauts getting lost on their way trying to get to a particular crater rim because they had a very hard time gauging distances on the surface. And this is something you can see for yourself. If you look at this picture here of a lunar lander on the moon, you'll notice that there is a object, a lunar feature behind the lander, and you can get your brain to be convinced that is either a small hill that's just right behind the lander or that it's a really big mountain off in the distance. And without the visual cue of the atmosphere, our brains can't figure out which of those two scenarios is the right one. Now, when it comes to astronomical images, we have the same effect. So here's an example of a Hubble Space Telescope image that looks three-dimensional. If you look at this, it really feels like this exotic world that you could explore. And this is an example of an astronomical image that our brains have a really easy time interpreting. There's the blue gas appears to be in the background, and then we have all these other overlapping features. And so this is an example of an object that our brain really has an easy time understanding, and it actually makes it more enjoyable for us to look at this. So sometimes people have asked me, can the Hubble Space Telescope see things three-dimensionally? And the answer is no. But many astronomical images, including the ones I make and the ones from Hubble, are images that do look three-dimensional because of the way color is used in them. And just to illustrate this idea, here is a picture from the Keyhole Nebula, and one picture in color on the left and the one on the right. And if you look at these two images, I think you'll agree that the one on the left looks a lot more three-dimensional. It looks a lot easier to understand than the one on the right. And for this reason, unfortunately, because I think they're often very pretty, black and white astronomical images don't get nearly as much attention as the color ones do. Now, another way in which our brains interpret color is that for temperature. For most people, we interpret red things as being hot and blue things as being cold simply because we're accustomed to red flames and blue ice. Now, of course, the reality is it's just the opposite, that when it comes to stars, it's the blue stars that are the hottest. But this is another example of how our brains can interpret color to mean another physical property, in this case, temperature. So I'll just mention that, as I said earlier, that optical illusions are often the result of our brain being tricked. It's trying to use our internal software to figure out what it is it's looking at. And this is an example of an optical illusion I saw recently that I thought was really amazing. So if you go to YouTube and look up the website Veritasium, which is a popular science website, there was one they did recently that I thought was really amazing. But there's lots of optical illusions on the internet. They're easy to find. So how do we use this knowledge when we create astronomical images? Well, the first thing we think about is what is the story? What is it that we want people to understand when they see our astronomical images? And so here's an example of the thought process that we went through. These pictures right here show the Triangulum galaxy. The picture on the left shows the Triangulum galaxy as seen just through an optical telescope. This is all data from the Kitt Peak 36-inch telescope. The image on the right shows the same galaxy, but now we have added data from the Very Large Array Radio Telescope. And you'll notice that we zoom in here that you can see all of this purple gas inside this galaxy. Now, the gas isn't actually purple, but we had to choose a color when we were deciding what color to make the radio waves be. Now, we chose violet for a reason, and that is violet is a mix of red and blue. And so we needed a color gas that had those two in it. And here's the reason why. So what you're seeing in the purple here is cold hydrogen gas. And if you look inside this picture, you will see these red clouds of warm hydrogen gas. And so it's the same hydrogen gas. The only difference between them is the temperature. Now, if I had used, say, like green for the color for the radio waves, not only would it look like someone threw up on the image, it wouldn't blend at all with the colors. And so it needs to blend so that people can understand that the gas that is purple is physically connected to the gas that is red, because it is the same gas. The only difference is the temperature. Now, the reason why I chose purple is because it's a mix of red and blue. And so it blends in with the red nebulosity, but since it has blue in it, most people will interpret that as being colder. So we want people to look at this image and have a natural intuition that what they're seeing is gas in the galaxy that is connected to the red regions, but is not as hot. Now, we're probably seriously overthinking this, but that's basically the thought process. Now, one thing I'll mention is that for the most part, when we create these color images, we are creating images that are designed to illustrate science that is being done. So we use the data from our telescopes to do precision measurements like the brightnesses of stars and calculate their temperatures and velocities and things like that. But sometimes we use these color astronomical images to do science as well. And so here's an example where by creating a color composite image that uses visual grammar, it actually allows us to interpret what's going on inside this three-dimensional object and to see features that might not have been visible before. So this is a picture of what's called the Iris Nebula. And after I made this image, I was looking at it closely, and I noticed that there were these little red blobs in it. And these red blobs are what are called Herbig-Haro outflows. These are jets of gas that are being shot out of young stars that are forming inside this nebula. And because of the colors of the image, we can see the dust, we can see the reflection nebulosity, and that gives us visual cues that help us interpret what's going on inside the nebula. So we can see that the Herbig-Haro outflows are deeply embedded in the gas, and that's why they're hard to see. Now, if I just look in the hydrogen alpha, it's a lot less clear what's going on because you lack that color reference that we use to help interpret the image. But in this case, what we were able to find once we looked in the infrared using the Spitzer Space Telescope is that there was a group of stars that were producing these two jets of gas that were being emitted from the nebula. So that's an example where we actually went the other direction. We created the color image first, and then that actually led to science. And I'd like to emphasize this point because sometimes people might think that it's science versus art. And this is an example of how art actually helps us do better science, that they're not mutually exclusive. Now, the last thing I'd like to share with you is just some of the stuff that we've been working on recently. I've been using this technique to actually search for young stars that are forming inside various clouds of gas inside our galaxy. And I'm using the telescope on the left here, which is the 4-meter telescope, is Cerro Tololo Inter-American Observatory in Chile. And this telescope currently holds the record for having the world's largest digital camera. And so here's a picture of someone inside the dome while observations are going on. And this right here shows the camera itself. The camera sits at the prime focus of the telescope where the secondary mirror would normally sit. And this camera has a 520 megapixels in it. So it is the largest digital camera that is currently deployed on a telescope. So this camera consists of 68 2K by 4K CCDs that are shown in the arrangement shown here. And just to give you a sense of scale of how big it is, this is the moon superimposed on this field of view. So myself and others have been using this digital camera to do surveys of large portions of the night sky. And I'm currently using this camera to search for outflows of gas from young stars that are forming in clouds inside our galaxy. So that's just an example of how the technology is improved. So the 64 megapixel camera nowadays is not nearly as impressive as it once was. Now, if you're interested in seeing any of the images that I've made over the years, most of my images have been made with telescopes that are now part of the organization called Noir Lab. And so if you go to our website, and go to the image gallery, you will see many of the images that we have made over the years. And I'll also mention that I've written a book with my co-authors, Kim Arcand and Megan Watsky, who work at the Chandra X-ray Observatory. And this book is called Coloring the Universe. And it's all about a lot of the things that I've talked about today, but in much greater detail. So it talks about sort of a behind the scenes view of what goes on at the professional observatories as we make our images. And so you can find this book at anywhere that sells quality books. In other words, you can find it on Amazon. So I will leave it there, and I will be more than happy to take questions from anyone that might have any.
This is Bob. I've got a question. Are there any colors that you try to avoid as you're going through the visible spectrum, you know, from red to blue? Are there some that are less appealing and less usable?
So it's important to know that our eyes have different sensitivity to different colors. And in particular, we're very sensitive to green and yellow. And so these colors can easily overpower other colors. And so when we make an image, we want to make sure the colors are balanced so it doesn't look like the image is just way too much of one color or another. This is what's called the contrast of extension in the art world. And so to make a balanced image, if you have green or yellow in it, you want to make sure that the other color, that it doesn't overwhelm the other colors. So we will use green and yellow for individual filters, but we just want to make sure that all the filters are scaled appropriately so the overall image doesn't have too much in it. One of the first astronomical images ever made had a lot of yellow in it. And one of my friends described it as being bilious or full of bile, which I didn't think she meant as a compliment. So I went and reworked the colors.
Okay, well, thank you. Are there any other questions from any of the people that are interested in night sky photography or astrophotography?
I've got one kind of a two-part question, Travis. I was curious what software you use. Is it some extremely technical software, or is it something that a common person would use? And then also, when you're creating the effect of depth, I was curious if you use opacity or layering or just the color selection or some blend of all of that to get a depth effect.
Yeah. So to answer your first question, it depends on the camera and the telescope that we use. But for many years, we've used a relatively obscure software package called IRAF, which was created by the National Observatories when digital cameras were first built. And IRAF can be best described as user hostile. It's very clunky, doesn't work very well. And if you ever see it, I recommend you run as fast as you can. But that is one of the pieces of software we use from some of the data reduction. We have moved away from IRAF in recent years and are using largely Python. And in fact, many of the newer cameras, like the camera that I just showed you, the dark energy camera, the 520 megapixel camera, all the data processing is done for you automatically, which is really, really nice. So once we have the processed FITS files, that's, they've been flat fielded and bias subtracted and various gradients removed out of the background, sky subtraction, et cetera. Then we use another really obscure software package called Photoshop. You've probably never heard of it, but it's another program that we like to use. And in this case, we do use Photoshop for the layering. So that's when first what we do is we translate the FITS files into TIFF files using a program we've written called FITS Liberator, which is a free software program that you can that is available to anyone. And then once we have the 16-bit TIFFs, we load each of those into Photoshop as a layer, and then we assign a color. We contrast, we adjust the brightness and contrast for each layer independently. We assign a color to each layer, and then we just simply use the screen image blend algorithm for each combination.
Yes, on record, I can speak.
So we do use Photoshop for also removing some of the cosmetic defects, like so CCD charge bleeds or chip seam defects or things like that. But that's our primary tool for the actual color assembly process.
I have a question about the time you said you get on the Chile telescope. You say you get maybe a day or two out of the 330 they have. Is that just small blocks of time here and there? That's not like wait a whole year to get one day?
So it depends on the telescope. So some of our telescopes are scheduled by the older telescopes are scheduled classically, and what that means is you request time on the telescope, and there's 2 deadlines a year to do that. And if you are granted time, they will say you have this night, or maybe you have half of this night. That's kind of the finest resolution they do as far as the distribution of time. And then when it's your time to use the telescope on that night, if the weather's good, you use it, and if the weather's bad, you're out of luck, and you just have to wait to ask for time again. Now, some of our other telescopes, like the Gemini telescope, are scheduled using what's called Q observing, as in QUEUE, like getting in line. And the way that Q observing works is when the proposals are reviewed, they rank the proposals from best to worst, and then they schedule the time in order of priority, and they on a night-to-night basis decide whose projects are going to be done on that night. So for example, what this allows is a lot more flexibility. So let's say you have a project where you need just the best seeing possible, and so if you have a highly ranked proposal, they'll wait until the observing conditions are really good before they will do yours. On another night, you may need photometric conditions where you don't have any clouds at all. For some projects, maybe you don't really care if there's a little bit of cloud or haze. It's not going to affect your science. And in those cases, the time is disseminated on even on the order of minutes. And so on the Gemini telescopes, we may only get an hour at a time, and they may just execute our project when the schedule allows it, when they may have like an hour long window that we can use. So that's kind of a long-winded answer to your question, but it really depends on the telescope. On the smaller telescopes, it's easier to get time. On the big telescopes like Gemini, we literally only get about 2 or 3 hours a year.
Yeah, and then one other just follow-up kind of on the same lines is, will you get time only? I'm assuming the slew time on these is not the greatest. So do you just take images where the telescope's already pointed, or does your time also include having to slew to what you want to go see?
So it includes the slew time as well. And so that is something that we need to account for, depending if, so many telescopes have multiple instruments on it, and transitioning from one instrument to another can take a few minutes. So for those telescopes, for most of our telescopes, we have software that's either used to do the scheduling or gives us an approximation of what's going to happen. One of the things that's really remarkable now with the telescopes that we use is how little the astronomer does. So in the case of the Gemini telescopes, you don't do anything at all. You write a little computer script that will tell the telescope where to point, what filters to use, how long the exposures will be, what dither pattern you want, and then when it's time for the project to be done, they just load the script and press go. The telescope focuses itself. It acquires a guide stars, et cetera, et cetera. So you literally have almost nothing to do, and often you don't even need to be there at all. So depending on the telescope, you may actually be present at the telescope, or you may be logged in remotely, but often you don't even need to be there at all. And you don't even necessarily know they're going to be doing your observations that night. It may not be until the next day when you get an email saying, you've got data, here's where you go to download it, that you even know it happened. So it's not as fun as the hands-on telescope, but if I never have to focus by hand again, that's fine by me.
Good to hear. Thank you very much for answering my questions.
You're welcome.
Very, very good presentation.
Thank you.
Travis, have you ever been impacted by satellites, the Starlink, those new setups like that?
It's becoming a serious problem. As more and more Starling satellites go up, they are putting bright trails across our images. This is a particular concern for wide field imaging cameras like the dark energy camera that I just described. And there's a new observatory being built called the Vera Rubin Observatory in Chile. And it's going to have a 3 gigapixel camera, a 3000 megapixel camera, that's going to see a 10 square degree field of view in one shot. So the challenge is if you have thousands of these Starlink satellites going around, what kinds of streaks will they make in our images? And so we're trying to work with companies like Starlink to help them build their satellites so that they are less reflective, so they don't make as bright as streaks or any at all. And then also part of the solution may be using software that can predict where the satellites will be at a particular time, so we can maybe avoid that part of the sky. But with tens of thousands of these, that could be very, very hard. I have been out at night when the Starlink satellites have gone by. I don't know if any of you have had a chance to see them. It's equally amazing and terrifying. It really does look like something out of a science fiction film when you just see hundreds of these streaking across the sky. And had I not known what they were, I think I would have been pretty darn scared the first time I saw it, because they are more prevalent near sunset and sunrise, just as most satellites are when they are still in sunlight before they go behind the limb of the Earth. But we have, professionals and astronomers have real reasons to be concerned about how space is going to be used. If we all laughed when Elon Musk launched a Tesla out into space, but it does, raise questions about, well, who gets to do that? Who gets to decide how this is all done? If someone decides to put a giant Pepsi, advertisement out in space, that impacts all of us. And we want to protect our dark skies and keep our, astronomy safe. And so that is a deep concern. And I hope that amateur astronomers and your organization and other organizations are speaking out on behalf of these issues, because we need to get the word out that astronomy is and will be impacted by these sorts of technologies.
Okay, thank you. Are there any other questions out there for Travis? I don't want to hog it, but I got one more question.
Go right ahead.
All these data sets are out there on the Noir lab sites and stuff. Would it be futile or entirely aggravating for amateurs to essentially bring those down to their computer, run Fitz Liberator on them, take them into Photoshop and play with them? Or would it, can you get anything good out of doing that? Or?
Oh, definitely you can, especially from some of these legacy surveys like DESI. You can download data. Unfortunately, it's not as easy as it should be. And that's something that will hopefully improve over time as they improve the interface, but it can be a little bit tricky to find the data products you want in the location of the sky that you want. So, there's a variety of surveys that have been done with our telescopes to cover large areas of the sky. So if you know what the sky coverage is, you can find objects in that field. For other objects, you need to go into the archive and just check to see if any observations have been done of that location with the kind of camera that you want. Unfortunately, especially for older data sets, the data may not be calibrated. They may not have been run through a pipeline to do all the processing. So for the survey data, like DESI, the data quality is very good. The data products are really, really well done. They have good astrometric solutions. They'll have all the different filters, and that's definitely something you can find and play with.
All right, anybody else have any questions?
No, I don't.
I got more if he's willing to answer.
Sure, go right ahead.
Go for it.
So what do you, I know I lived up in Anchorage for a couple of years. What do you do for night sky?
What do I do for night sky? Well, so I love Alaska, but we don't have good night sky. Certainly not.
Oh yeah, I know.
Like we have in Arizona. It's a beautiful place, and I love living here. But the hardest part is that of course, for half the year it's light out all the time, and then for the other half of the year, it's often cloudy and it's pretty darn cold on the nights that it is clear. And one of my favorite stories is when I first moved here, the local astronomy club invited me to come out for a night of observing with them. And so, we're out just doing some, fun small telescope observing of things or this and that. And at one point, one of them said, "Oh man, not again." And I said, what's wrong? And he said, "Oh, the aurora are starting up again." And they were all disappointed because it was going to ruin their astronomical observations. And I was like, oh my God, this is why I'm here. I want to see the aurora. So, but that is a funny reality. Sometimes the aurora pop out and does impact things. So Alaska is not the best place for astronomical observing. It's actually pretty terrible in a lot of ways, but we do have the aurora, especially as you get further north, and that's pretty darn amazing too.
Yeah, the aurora was nice. So I enjoyed living up there, but yeah, the winters.
Oh, you
were a
lived
little
up
bit
here?
long.
Where did you?
Yeah,
did you
lived
live
in Anchorage. Yep,
Oh,
lived in
okay.
Anchorage.
Okay.
So, yep.
Yeah, so you know the deal.
Yep.
Yeah.
Very cool. Bob, you mentioned that Travis has some Alaska photos.
I think he showed some of them in the
In the beginning?
in the presentation,
Okay,
the fish islands of the
Right.
Aurora and stuff like that. That's
Yeah, I apologize. I don't have more. You know, the Aurora photography I've done, because we have a digital planetarium, I've been focused on creating time-lapse films of the Aurora, just to share with people what it looks like. So the nice thing about shooting fisheye is you don't have to point it. You can just point it straight up and it gets everything. But I haven't done as much like traditional like rectilinear photography.
Okay.
There's a lot of amazing Aurora photographers up here, so it's hard to compete with them.
very good.
But you know, Aurora photography is very much like any astronomy. 90% of it is just perseverance. You know, if you for the Aurora, you just never know when it's going to be good, and so you just have to go out night after night after night and just hope for the best.
Now, does it normally occur in the wintertime then?
It occurs year round, but of course during the summer it's mostly light out, and so it's harder or impossible to see. For reasons people don't really understand, the aurora tend to be a little bit stronger around the time of the equinoxes, and so we've actually had pretty good aurora for the last few weeks. And but at this time of year, the light is returning rapidly, and so within a few weeks we won't be able to see anything at all.
And do you typically take videos of these or?
So far, what we've been doing lately, I mean, as the technology improves, it's changing. Our most recent project, we were doing 3-second exposures, and we just got a giant memory card attached a car battery to the camera, just set it up and it just lets it run all night, and the card can hold I think like 14 hours worth of photographs at 3-second intervals. And so then we make time-lapse movies out of that. There are new digital cameras that are actually doing pretty good at video frame rates, but we haven't found a solution yet that has a fisheye lens in the way that we want without some sort of obscuration. So the Sony A7 cameras are very sensitive detectors, and so those are ones that people are starting to use up here to do actual videography of the aurora. It's pretty amazing. I mean, even an iPhone nowadays can do a really good job. It's amazing.
Thank you.
Yes.
Does anybody have any more questions?
One more, if you don't mind. Did
Sure,
you
go right ahead.
did you originally set out going to school for this, or did something change you along your way that took you through this path?
You know, this was never a career goal for me. And, you know, I'll say that this is really still just something that's kind of on the periphery of what I do. It's not at all related to my research or the teaching that I do, though obviously I do teach a lot about it. And I actually have a lab in our astronomy classes where I give students an opportunity to create their other color images. It's kind of, you know, it's sort of, I guess you could call it a hobby, but I guess it's sort of in the same hobby in the same way that commercial pilots, you know, fly Piper Cubs on the weekends, right? It's in their blood and they just need to be in the air. And so I love the color images. It's just, you know, it's something that really connects with people. And it's, you know, not many people read my research, but many people have seen my images. And so hopefully, you know, that's what makes it fun. And it's fun to talk with people about it. It's also especially fun whenever I see one of my images pop up somewhere unexpected. One time I was in Milan in Italy, and I was on a subway train, and there was a person reading a magazine, and one of my pictures was in it. And that was just like the coolest thing. It's just so fun to think about that, you know, these images are all over the place, you know, especially with the internet, anyone can get them. And it's just fun to be able to share the universe in this way.
A dumb question, maybe, Travis. What about other spectra of heavier elements and molecular spectra? are those mapped and put on a picture somewhere, or are they just too concentrated near the stars to make any sense?
So for the most part, we use filters of elements that produce particularly strong lines so that we can see them in nebulosity very far away. So obviously hydrogen, since it's so abundant, but hot oxygen and hot sulfur atoms. For the densities of atoms and the temperatures at which they tend to be in space, you can actually see them relatively easily, even though they're not nearly as abundant as hydrogen and helium. But when you get to heavier elements, certainly things beyond neon, these are elements that are just in such low abundance in the universe. They're just not something you can hope to detect.
Now, I found it intriguing that on Europa, they were looking for signs for water and weren't looking at spectra to analyze it, but molecular resonance. And I was kind of intrigued by that.
Yeah, so certainly things like if you're looking at an atmosphere of a planet or a moon, where you could hope to detect like water vapor or carbon dioxide or oxygen molecules, those are opportunities where you could actually detect these molecules. And in that case, you're actually seeing how they're absorbing starlight. And so that's, absorption lines in that sense are easier to detect than emission lines, because to produce emission, the molecule has to be hot. And for the most part, you only see molecules in atmospheres, whether they be in atmospheres of cool stars or in planets or moons. And so, it's just very hard to detect molecules. Now, I will say you can detect molecules in the radio, and that's something that's done all the time using radio telescopes to look at clouds of gas out of which stars are forming. And an incredible amount has been learned that way. That's a field called astrochemistry, which is the understanding of how molecules, chemical compounds and molecules can form in space.
Thanks, Travis.
Sure.
Yes, I really enjoyed this tonight. This was fascinating.
Yes,
Well, thank you very much.
Thank you.
Does anybody else have any more questions?
I'm done. Thank you very much.
Okay. Well, thank you all for inviting me. It's a pleasure to talk with you all. And
Thank you very much.
I'm hoping to come down to Kitt Peak in June. Of course, none of us have gotten to travel much recently. And so I'm hoping to actually get to go back to a telescope sometime soon.
Very good. Very good.
So,
Well, if you can get us in the back room, give us a call. We'll go with you.
That's right. That's right.
well, I'm envious of your star parties. We don't get to do those up here. Certainly
Yeah.
not for the months
you
of
go.
April through August.
Yeah, well, you got
If you're-
some great fishing.
Right. If you're coming,
We do have that, yes.
If you're coming down here, just let us know, and maybe we can arrange a star party. And you can,
That sounds great. I'll definitely do that.
all right.
All right.
Sounds good.
Thank you.
All right. Well,
Bob.
it's a pleasure talking with you all. Take care.
Okay.
Thank you
Bye-bye.
very much.
Bye.
Well, everybody, I want to thank you for joining us tonight. And does anybody have any questions for me or Bob or John Klein or anybody of our officers? Right now, we have Amen, who is visible on my screen anyway. Amen is now heading with Larry, the astrophotography group. And I think they're having fun based on the emails I've been seeing popping back and forth. And I think it's great that we can have a group and answer questions and help each other out. And that's what this is all about. So, and again, I want to go.
Hopefully it will take off here.
Yeah, I think it will. I think it will.
Yeah,
Once again, yeah, probably. Yes. So, it's been fantastic that we've been able to have these Zoom meetings for the last year plus. But I think we're all kind of tired of them. I think we all kind of like to see each other once in a while, other than see voices and maybe a flash of light at a star party. So on May 4th, we're going to have this picnic, and I'd love to see as many people show up to it as possible. Like I said, we're going to try to do our social distancing, have a good time, and if anybody wants to share anything, please step forward and let me know. And if you want to have a 10 minutes to talk about something, 20 minutes, I don't care. Just let me know and we'll make arrangements for that.
Hey, Rob, what time is it again?
It's from 6 to 9.
Okay.
Okay, and it was actually at 5, but then I realized we have people who work, and by the time they get home, it's going to be a rush to get over there at 5 o'clock or whatever. So we moved it to 6, and it's a potluck picnic. We're not going to be grilling anything, but the club will be supplying the paper plates and the silverware and bottled water. So if you want to bring anything else to drink, that's your choice. So, but hopefully we're going to have a good time, and we got lots of room. And be sure to bring your folding lawn chair and relax, and let's get together and see each other's face visually, physically, instead of digitally. So,
I had a question. John, have you had any interest in outreach or things from the library or other groups? Has that started to come around, or are we still?
No, I was in the library yesterday, the Northwest Regional, and you can only stay there for a few minutes anyway. There's no way you can have a meeting where you put a lot of people in a room unless you really cut it in half or even a quarter size. And that wouldn't be very rewarding to be able to speak to 4 or 5 people. But other outreach, no, I haven't. I'm open.
John Hyatt has been working on that.
Yeah, that's the John I met. I should have.
Oh, I'm sorry.
John, well, it's okay, John Klein.
It's okay. We got two things going here.
Just got
Yeah.
Bob's and.
In fact, I just was in touch kind of over the last week or two with the lady who's at the Peoria Library, and they're getting close. So she'll keep in touch. I just today, after about a week or two, got a response from the school teacher down at just south of me here.
Marley Park.
Marley Park, yeah, Marley Park School. She's second grade level. And I guess you guys had worked with them in the past, and they're also getting closer, but I suspect that might be more toward fall. And then there's one Cub Scout group that also I just got back in touch with, and they're basically done at the end of April. The timing didn't quite work out, so we'll kick that one to the fall. So I got those 3 kind of all in progress. And I'm guessing the Peoria Library is likely to be the earliest one. Was the Marley Park one, Bob, did that coincide with the Observe the Moon night?
Yes, yes.
Okay, I
Last,
didn't-
We went to the school,
I'll let my wife talk.
yeah, we went.
Well, I could say it.
At the gym.
Hey, she can't talk unless she's on camera.
Yeah. Okay.
We went to the school, and then as we were there, we kind of decided, well, geez, maybe we could do the moon night here across the street at Stark. But we went to the school like a month ahead of time, and then then we asked the teacher to help us get the word out. And I guess as we were there, we told the kids, because they were so interested, we're gonna come back and show you the moon.
Yeah.
So
Yeah.
that's kind of how that all kind of tied together.
Right. Right. That was our first year for doing the Observe the Moon night, and our first time to actually do an outreach to the school. So it was fun. Michael Whiteberg and I had a telescope set up, and that worked out good, although it was 105 degrees. Yeah, Bob Carolyn was there. Yeah, but we did get to see the sun, even though there was no activity going on, but the kids were amazed. And Janie did a bunch of little programs with the kids, and we had fun. We had 150 kids.
Yeah.
Between the 4 classes. And then on the Observe the Moon night, this Jennifer, the teacher, she really got the word out. And we had well over 100 people that showed up, coming and going, and they had a big pizza party in the park, and it was fun. It was fun. And I don't, Bob, you give me a guess how many telescopes we had there that night? We probably had 15 telescopes there, probably
Yeah, I would have guessed about 10 or so, yeah.
10 or 15. Yeah. Yeah, it was good. And what was really great about it, I sure hope this is true in September this year. I haven't looked, but we not only had a perfect moon to look at, but in that time of year, Scorpio was up there in full view, and we had Jupiter and Saturn on one on each side of the moon. So you could take your telescopes and go back and forth, and the people were just amazed.
Yeah.
It was fun. It was fun. So anyway, yeah. So I saw that email today, and I thought, oh boy, good, we got her. She's still interested. So
Yeah. And to go along with that, Bob just recently, I've kind of had, he's given me emails of people when they've expressed, like when they join the club and they have some interest in outreach. So I've got that all kind of set up in a Google list so I can start to kind of communicate with them as something starts to show up. I think, I don't know, Bob, I guess I got maybe 10 or 15.
yeah,
10 or
about 10 or 15 emails I put. I went through our entire list of applications and found them. One of these days, I'm going to find a club software where we can actually have all that information to our disposal and easily query it. But I haven't found that yet. You know,
Say that again.
right now it's all in a folder. All these applications are in a folder, so I have to go through all these folders, all these applications to find this information. See, and I love to have it all in a database on the computer, and that's so that you can say, okay, I want to know who does this, who does that. That's the computer world I live in. So,
Yeah.
But I haven't found an application we can afford. There's good ones out there, but we can't afford them. So,
Okay.
Okay.
all right. Well, as that's all, anybody else have anything else to share? Paul, have you heard anything about any activities?
I have a question.
Oh,
Where was the speaker located? Someplace in Alaska?
Anchorage.
He's
Yeah,
in Anchorage
Anchorage.
right now. Okay. That's so cool.
Yeah. Well, see, that to me is people don't like Zoom and stuff like that, but it
Yeah.
allows you to have people like that
Absolutely.
present to us. So my proposal when we're back to the church is we still may want to have zoomed in speakers from across the nation if we can find good ones.
Yep.
But we're there to have coffee and watch it on a big screen together. We just have to figure a way for people to answer or ask the right questions because or stuff like that. So
right. We can work. That's minor. We can work that out.
yeah, we'll work that out. So
Yeah.
I don't know
That's-
how you found him, but he was super professional. Bob, I don't know where you found him.
I kind of piggybacked off the East Valley
I asked.
telescope. Remember, I got that when I first talked to him. He wrote back to me and he said, "I hear there's bad blood between the West Valley and the East Valley," and I was petrified. I thought that somehow we'd piss somebody off or something.
Not at all. Not at all.
But then what I said is I missed the emoji at the end of the sentence that it was just kidding, So,
Oh, okay.
but
He really was great. That's one of the most practical talks about the subject I've heard.
yeah,
Right.
I really enjoyed
Right. He explained the whole thing better than I've ever heard.
right. I thought, his analogies and the way he put the subjects across, I thought was great. So, yeah.
Cool.
So thanks.
I was just impressed with the connection. The connection was great.
Yeah.
Yeah.
Yeah. To think he's up there and we're down here, and yeah.
Mhm.
I do want to share. I received an email today from one of our members who said he will not be able to make it to the picnic, but he did say that he is glad that the club did do these Zoom meetings during the pandemic and kept us together. And he thought it was a fantastic thing. And he was a beginner, and he also enjoyed every one of the sessions that Richard, I think it was Richard Bell in Kalamazoo did for astronomy, beginning astronomy. So a lot of people, I have received numerous comments from people that enjoyed those sessions.
Yeah.
And I'm gathering all the PDFs and the links to all the meetings, and we're going to make it as a group link off of our website.
Okay.
So,
Yeah, I think we need to also thank Deb Blykamp, because she saved us essentially $15 a month by
Right.
letting us ride on the school district, you know, so on the Zoom
Right.
membership, you know, so.
I
Thank
will
you, Deb.
personally thank her for you. She's about 7 feet. She doesn't do like Janie does. Speak, Bob, if you actually move your mouth and let Janie talk, then we'll think it's her voice coming through you.
Oh, is that right? Yeah, well, we can try that sometime. Yeah.
So she and Debbie's right next door. The irony is that somebody else in the family has a Zoom account. I won't say who it is, maybe for the camera on, and wasn't technologically proficient enough at the time that he got the account. So she jumped in. So yes, I will thank her proficiently for all of us. She's
Okay.
Thank
2 feet
you.
away
Thank
from
you.
me.
It's great.
Thank you. So in other words, if we have to do Zooms again, we have somebody we can fall back on.
That is correct. And now there's 2 of us that can do it because I use it with my patients.
Very good.
Mhm.
Very good.
One last 10-second observation. What you guys are all participating in right now probably saved research is being done right now. But the 12-step community was unable to be together throughout the entire world, which is their primary source of support. And somewhere between 100,000 to 500,000 lives were probably saved by the Zoom Corporation and others like it, to allow people to communicate in a way that, with the prevalence of phones and iPhones around the world, that where people were able to say, we lost a lot of people in this last year because of their inability to stay connected. So my wife's efforts as a school teacher, mine as a counselor, were helped because of technology. And I was an anti-technology guy for many years, because I didn't understand it, but its power is amazing. So what we're experiencing is a microcosm of what the entire world's had the opportunity to use for the last year.
Right. Yeah, that's been fantastic. Yeah. And I'm glad Zoom has stayed away from the other tech companies and just let everybody do their thing and open the doors so everybody can do it.
And also, I haven't been participating because I never understand speakers anyway. You guys, this was really professional. I'm really impressed.
Thanks, Bob.
It was
That was
good.
really good.
Not just the
Okay,
speaker,
wow.
but like you guys are really well coordinated, get it together. I just, impressed.
Maybe
That's-
Robert could put on a
right
collared
there.
shirt.
Yeah.
But
Oh, do you know about the collared shirt thing?
Oh, yeah. Mhm.
I made Bob, because I tell him, why aren't you wearing a collared shirt?
Well, neither is the vice president there either, so don't get on me.
I can't yell at him.
I haven't turned on my AC yet. That's why I'm stripped down like
Yeah.
this.
All right. Well, gentlemen, is there anything else tonight? I want to thank you all for all the hard work you all do.
See you at the picnic.
All
Yeah,
right.
see you at the
All
picnic.
All right.
see
All
ya.
righty.
See you there.
Thanks again.
I need to know what you're bringing, and I need to know that you're coming. So,
My knife and
drop me
fork.
a line, all right? All right.
All righty.
We'll talk to you all later.
Bye.
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 Bye-bye.